In modern number theory, a rich source of very interesting problems lies at the intersection of physics and number theory. So one noteworthy example is there, of course, the quantum unique ergodicity conjecture, which loosely speaking says or is concerned about the distribution of a particle on a given surface. Or even more loosely speaking, you can think of, we have here this particle on a billiard table, and then we are asking ourselves, okay, how likely is it to find this particle at any given place on this surface? Now you might ask, how is this related to number theory? And this really comes from the fact that we are not looking at the classical particle, but a quantum particle, and there we have this Schrödinger equation. So this Schrödinger equation is has this Laplace operator, and in this connection we also have in number theory those Heck-Maas Cusp forms, which are eigenfunctions of this Laplace operator. And there we can really see how this connection to physics and number theory comes into play. In number theory, we often have the advantage that there is additional structure given, and so we can actually prove things rigorously. So this additional structure, for example, is often are those Hecke eigenfunctions, or we have this Hecke operator, and those Hecke-Maas Cusp forms are actually eigenfunctions also under this Hecke operator. And one can use this information to deduce things like quantum unique ergodicity. Now, today, as you maybe saw in the title, we are not necessarily concerned with those Hecke-Maas Cusp forms and quantum unique ergodicity conjecture, but something called the random wave conjecture, which has a similar flavor. Okay, so the random wave conjecture, introduced by Berry in 1977, says that on a negatively curved surface of finite volume, that those Laplace eigenfunctions tend to exhibit Gaussian behavior as the eigenvalue tends to infinity. Okay, so maybe to convince you how this is related now with those mass forms, so my Laplace eigenfunctions, if we look at the Fourier expansion of a mass Cusp form, then we have the following equation up to constants, that the Cusp form is given as this sum over the Hecke eigenvalues, so lambda f of n are the Hecke eigenvalues, and then here we have some k-Bessel function and the spectral parameter which will go to infinity, when one says, okay, the eigenvalue goes to infinity is when the spectral parameter goes to infinity, is given by R. Now, if we compare this with a so-called random wave, we can naively think of it as something of this form. So we see they look quite similar, but rather than those arithmetically defined Hecke eigenvalues, we simply have random coefficients or coefficients Cn that are, say, randomly chosen with uniform distribution in -1, 1. So maybe now, if you formulate this random wave conjecture again, you can think of if the eigenvalue, this R, tends to infinity, then those tend to behave quite random. Actually, another formulation of the random wave conjecture can be given in terms of moments. So if we look at the fixed compact subset of the full fundamental domain, okay, so we look here at SL2Z, what the upper half plane, and then we look at the suitably normalized Hecke eigencusp form, then we have that the nth moments of my mass cusp forms should agree with the nth moment of a Gaussian random variable as the spectral parameter tends to infinity. Okay, so this is simply another formulation of this random wave conjecture where we actually can get our hands on, so to say. Now, in this talk, we are not necessarily concerned with mass cusp forms, but an analog in number theory, namely the holomorphic Hecke eigencusp forms. So rather than being an eigenfunction of the Laplacian, we are, satisfy another differential equation, Cauchy-Riemann differential equations, and so we are actually holomorphic. So there's maybe not directly this nice relation to physics, but often those conjectures like quantum unique ergodicity, random wave conjecture can also be formulated for the holomorphic Hecke cusp forms. And that's what we are looking at in this talk. We are in particular interested in this fourth moment problem. Okay, so we are looking at the fourth moment of holomorphic cusp forms. And the reason why we look at this fourth moment is really because we can, let's say, get information on these fourth moments via L functions. So after an application of Parseval, there is the very nice formula of Watson who relates a triple product of cusp forms, Hecke eigencusp forms, to this triple product L function. So here in the beginning, we had the fourth moment of cusp forms, holomorphic cusp forms, and we relate it to a first moment of a triple product L function. And now for an analytic number theorist, here we come into play, so to say, and we are using techniques to estimate moments of these L functions to actually get a result for our original problem that is related to the random wave conjecture. So maybe in the beginning, how difficult is actually this moment problem, right? We want to have a quite good estimate, or maybe even in best case, an asymptotic for this moment. And usually what one does is one looks at how large is the family and how complex is the L function. So here in this case, we're averaging over a family of k L functions. So G is running over a basis of Hecke cusp forms of weight 2k. So there are k elements in this family. And the L function, so this is a degree 8 L function, has an analytic conductor of size k to the 6. So this implies that the ratio of those two quantities is actually 6. So we can compare this with a 6 moment of zeta. So evaluating this moment is, so to say, at least as difficult as evaluating a 6 moment of zeta, which is, of course, not known or difficult depending on which conjectures you assume. One very important remark at this point is that in the analogous problem of Hecke mass cusp forms, okay, so not the holomorphic case, but mass cusp forms, that we also relate this fourth moment problem to a triple product moment like this, but there actually the logarithmic ratio is 4. So the ratio is smaller and is kind of comparable to a fourth moment of zeta, which is doable. And indeed, of course, it's still more difficult in that case than a fourth moment of zeta, but Butkin and Kahn showed under the assumption of the generalized Lindelöf hypothesis actually an asymptotic for the corresponding moment problem. But our case of the holomorphic cusp forms, okay, is harder because we have here this analytic conductor of size k to the 6, which gives rise to a ratio of 6 rather than 4. And we are trying to attack this problem and see how far we can get, what is the best estimate we can hope for with our current technology on this. So maybe let's look quickly at some moment problems so that I really convince you that this is related to moments. If we look at the moments of zeta, then under the random matrix theory, we can get a precise asymptotic. Similarly, we could also look at quadratic Dirichlet functions, and we average over D, and then we also get a precise asymptotic. And now you see, in our case, we are not averaging over T or the discriminants D. We average now over cusp forms, and we have here this triple product L function. But in principle, those problems fit into the same setting. Now, for zeta, we can actually say quite a bit, right? With random matrix theory, as mentioned already, we know the precise asymptotic. Also, under Lindelöf hypothesis, we can quickly estimate this zeta by t to the epsilon and get also this quite sharp bound t to the 1 plus epsilon. But then in 2009, Soundararajan had this wonderful paper and proved almost sharp bounds for the 2elf or the all moments of zeta. Okay, so there was a t times log t raised to the power L squared plus a tiny epsilon. And actually Harper improved on the techniques and actually got rid of the epsilon. So under the assumption of Riemann hypothesis, we know sharp bounds for zeta. And we also have the corresponding lower bound. So what we're really missing in the case of zeta is only the constant. But of course, that's still a very difficult problem. Now, we are not looking at zeta, but we are looking at this first moment of the triple product L function. So what are the predictions? Also, we could apply random matrix theory or the random matrix conjectures. And actually, of course, it should agree with the random wave conjecture. And in both cases, we get that this first moment should be asymptotic to the constant of 2. Okay, so where is this 2 coming from? This is exactly when you evaluate the fourth moment of a complex Gaussian, you will also get this constant 2. Also under Lindelöf, we could get quite quickly, or generalized Lindelöf, we get quickly the bound k to the epsilon. But note that this k tends to infinity, right? So this is still diverging, while we expect the constant 2. And our goal is now to see, okay, maybe we can use this RH and improve on this k to the epsilon, similar to what Butkin and Kahn did in the mass form case, where they showed a precise asymptotic. What can we do? Of course, we don't expect the precise asymptotic, as otherwise we could also get an asymptotic for the 6th moment of zeta, but maybe we can improve on this conditional Lindelöf bound. So our idea is actually to apply those techniques of Soundararajan and Harper that are very robust and also apply not only to zeta but different L functions, and see what we can get in this case. So let's quickly review how they approach their problem. The first instance one can think of is zeta, and this Selbach central limit theorem is telling me that the logarithm of the zeta is approximately Gaussian with means 0 and variance 1/2 log t. Okay, so why should this help us? We could make this quick heuristic, and we have the following computation for a usual Gaussian random variable with a given mean mu and variance sigma squared. Now, if we actually apply this heuristic to our case of zeta, okay, so log of zeta is now my Gaussian random variable, my mean value mu is 0 and my variance is given by 1/2 log t, then we plug this in and we get exactly what we expect. We get this log t raised to the power L squared. So this is how one could quickly get a heuristic for the expected size of the 2-elf moment. Now, of course, the difficulty in this entire problem is to make this idea work and to make it actually rigorous. And one of the important steps is actually this wonderful formula of Soundararajan, which shows that you can approximate the logarithm of zeta very well by short Dirichlet polynomials over primes. Okay, so we have here this formula, and one should think of maybe as zeta as given in terms of an Euler product. Maybe I should go a little bit away from 1/2, but roughly you think of zeta as an Euler product, but it's easier to work with Dirichlet polynomials. You take the logarithm. And here we see the corresponding thing, or a corresponding formula also holds for our triple product L function of interest. Of course, because we are looking at a degree 8 L function, the corresponding approximation is also more difficult or simple. But the principle is the same. We have here the primes part, here we have a prime squared part, and a prime cubed and so on don't contribute much and go into a negligible error term. Now, if you recall, when we look at moments of zeta, we are averaging over t. So the actual source of randomness that we want to detect, right? We are kind of looking at a heuristic coming from probability, and the source of randomness are here my coefficients p to the minus it. And if I average over t, then I kind of should see this as taking the expectation, and I should deduct my randomness. Now, in our case, we are not averaging over t, of course, but we are averaging over my Cusp forms g. So in this case, the analog of this coefficient p to the minus it are those Hecke eigenvalues lambda g of p. And those are my source of randomness. Now, let's try to do a similar heuristic as we did in the case of zeta. Now for my triple product L function. At first, we have to evaluate, okay, what is the mean value, what is the variance? In the case of zeta, we had a mean value of 0. Here we actually have a mean value given by this quantity. Okay, and you can see this, for example, if you average over g, those coefficients lambda g of p are on average 0. Also lambda g of p squared is on average 0. So the only thing that is left is coming from this constant -1 times this factor here. So this is my mean value. On the other hand, the variance is given by this quantity. You can also see this if you square the corresponding thing and then average again over g, you get roughly this variance. Now we do a similar heuristic as we did in the case of zeta. So we apply our formula which we found for a random variable with a given mean value mu and variance sigma squared. We plug in everything, and we see that here this average over the triple product L function in the end gives exactly rise to L1 sim squared squared. Okay, and this is actually great because in our original problem, we were looking exactly at a quantity like this, and we had here this factor L1 sim squared of f in the denominator. Okay, and it's a very nice feature that this L1 sim squared actually pops out after this mean value and variance computation, and everything cancels nicely. And so to finish this talk, what we end up with as a result is that actually the fourth moment of those holomorphic cusp forms is bounded. So we cannot show the precise asymptotic, right? We never expected to be able to do this, because otherwise we could also solve a 6 moment of theta, probably. But we can go beyond Lindelöf hypothesis. We show that this is actually not diverging, it is bounded, and that's kind of another instance or another indication that also the random wave conjecture in this scenario should also hold. Thanks for your attention, and I'm happy to answer questions.